All right, so there's one on the homework like this, but I still want us to look at one like this. See if we can figure out which of these graphs might be log base 4 of x. And to do so, it might help to look at the table for log base 4 of x. You don't have to. There's other ways to do it, but I feel like that's kind of the easy way. So, do we have any instinct on which one of these it might be? A, B, or C? Or are there any that we could rule out? Okay. So if we don't have any clue, what we're going to do is we can start this off just like if we were asked to graph it ourselves. If we look at our base of 4 and think about what the logarithmic parent function is going to be if we think about 4 to the x, so that we could get our table so that we could look at log base 4, just to see which ones match up. That's a fine way to do it, to figure out what our x's and y's would be. So if we're looking at 4 to the x's we normally pick are things like our -2, -1, 0, 1, and 2. And if we're looking at 4, we'll have 1/16, 1/4, 1, 4, and 16. So that gives us our exponential, and that leads us to our logarithm, because we know we're going to have our 1/16 -2, our 1/4 -1, our 1, 0. We could continue on, but honestly, that is enough to figure out which of these graphs is going to fit. Which graph do we think is going to fit this? Which one of these graphs has a point at 1, 0? Only 2 of them do. Yeah. A and C both have a point at 1, 0. So, like, we know for sure at that point it's not B. And if we look at our other 2 points, our 1/16 and 1/4, those are little guys. Those are these guys. We're at -2 and -1, whereas on A, they're higher. So my 1/16 is up here at 2, and my 1/4 is up here at +1. So this is not the same. So it's going to be C. So when we're looking at these, feel free to look at our parent table, our parent function, to help us figure out which one it's going to be, because this is the guy we're talking about. And then we have 3 questions about this particular function. We want to see our domain, our range, and where is the asymptote. So what is our domain of this graph here? So definitely it's going to positive infinity, but what is our left side of it going to be at? Does it go all the way over to negative infinity, all the way over here? No. Where does it stop? At 0. So our domain is going to be from 0 to infinity. And in fact, that'll be our domain for every logarithmic parent. So every log that doesn't have transformations is going to be 0 to infinity. What's our range on this one? Negative infinity to positive infinity. And again, that's going to be our range for absolutely every single logarithm. Every single one. Where is our asymptote? It's at 0. Is it x equals 0 or is it y equals 0? X. Because if it was y equals 0, it would be right here. That's exponentials. So logarithms have x equals 0 as our asymptote. X equals 0. Okay, we don't typically draw our asymptote in on parent functions, but we can. It's not wrong. It just makes our pages a lot more complicated to look at. Okay, questions on this one? There's one like this on homework 1. I just wanted to do one very similar to it so we could practice it. Okay. So we are going to be in our notes packet. We're going to keep working with our graphing on logarithms because we have one transformation we haven't seen yet, and then we need to do somewhere where we have all our guides all at once. So we did 1 and 2 yesterday, so let's look at 3. Chalk. Next one. And again, we are going to wind up with 3 tables on this. 2 graphs, but 3 tables. So if you ever want like colors or colored pencils or highlighters or anything like that, I have like tons. I'm more than willing for you guys to use them. I can get those out at any point. That one's just going to keep rolling off. I was like, I have markers, I have colored pencils, I have whatever we need. So we are asked to graph f of x, which is log base 3 of x, and our g of x, which is 2 log base 3 of x minus 2. So what I notice and what I see is that on both of these, which they always will, have the same base at 3. We will never ask you to do different bases on the same graph. That's just cruel. So that means we start by looking at our exponential piece that has the same base. So the table we're going to draw that we do not graph has the same base as an exponential. So the first table we're going to draw is that 3 to the x. Just making sure it shows up. It's very pale, but we're not graphing it anyway. I can make it slightly darker though. There we go. 3 to the x. So we're going to make the table for 3 to the x, but we are not going to graph 3 to the x. This is when we pick our x's to find our y's, but we just need this as a tool to help us find our log. So when we're picking x's, we usually pick a good view of the middle where we'll use our -2, -1, 0, 1, and 2. It is not a law. It is not a math rule. It is a very firm suggestion because these are good points and they're easy to use and they do not make things harder than they need to be, and it gives you enough points. I highly, highly strongly recommend these 5, but as long as you have at least several, you do you. It's your graph. But you need to have some points. You need to show me how you get your picture. Just come over here and going, whoo, that's my graph. Just doing that? Not so much. Give me details, how we get there. So to get our y values on here, we put these x's into our exponent here. So 3 to the power of -2, we get 1/9. 3 to the power of -1, we get 1/3, and you can type these into the calculator. Like, it is absolutely valid to use the tools at our disposal. 3 to the power of 0 is 1. Anything raised to the power of 0 is 1. 3 to the first is 3, and 3 to the second is 9. Every single exponential function that's apparent like this has an asymptote at y equals 0. Again, not graphing that one. This is a tool that we use so that we do not have to sit here and go, okay, log base 3 of 2 or log base 3 of 1 and trying to figure out that stuff. So we do not have to calculate 5 to 7 individual logs. We use the exponential. It saves us work. So to get our log base 3 of x, this is when we remember that exponentials and logs are inverses of each other. So anything that was in the x column on our exponential becomes our y, And anything that was in the y column becomes our x. So I'm going to take everything from the y column and put it in the x's. And I'm going to take everything from the x column and put it in the y's. If it was a y, it becomes an x. If it was an x, it becomes a y. So my x's are going to be our 1/9, 1/3, 1, 3, and 9. And my y's are going to be our -2, -1, 0, 1, and 2. And just like with our points, everything that was an x becomes a y, and everything that was a y becomes an x. So our asymptote turns into x equals 0. This is our parent function for the log. So this is going to be the first piece that we graph. With our parent functions, I will almost never graph the asymptote because the asymptote is our axis. So it's this big bold line that's on our graph already there. So this is our line that we cannot cross. We cannot Kool-Aid man our way through the axis. So don't cross this line, but I don't need to draw the asymptote in on our parent function. But I am going to plot up my points. We are going to come through here, and I'm going to put my point at my 1/9, -2, which is going to be right in there. My 1/3, -1 is going to be right about there, and they're very close together, and that's okay. And then we're going to have our 1, 0, our 3, 1, and 9, 2. This is our parent function, our f of x, which you can just label as f of x, or you can do this in light pencil versus in dark pencil. I can get you colors, whatever you want to do to make it very clear which one's your parent and which one's our transformation. I don't care how we clarify what they are, just make it clear. It can just be labels, it can be colors, it can be thick pencil versus thin pencil, it can be pen versus pencil, black pen versus blue pen, I don't care. I have a full rainbow, a variety of several rainbows that I will diversify with color. Questions on our parent? Because then what we need to do is we need to do our transformations. So to get our transformed function, we're going to take our x values and add h and y times a plus k, because graphing makes us yak. But that means we need to know what a, h, and k are. So we're going to look at our function here, our g of x, and see if we can figure out what our a, h, and k are. What do we see? What do we notice? We've got this phrase in here. So, so that's which letter? The H. Our H is going to be a positive 2. It is always the opposite of that expression, which means which direction is that going to push our graph? Right. To the right. We are going to go right 2. That is not what I meant. We are going to go right 2. What other piece do we have up here? The 3. Yeah, we have, no, not the 3. The 3 is our base. We've already used that guy. That's this guy here. This 2. Yeah, the one that's multiplied out in front. This guy is our A. What does that mean is going to happen? What does an A of 2 do? Stretch. Good. That's when it's going to get taller. It's a big kid, so it does big kid yoga, so it's going to get taller. So when we apply these transformations, we're going to take our parent functions and apply these. What is our K for this one? It's not the 3. Look at where k is on our form. So k is over here. What's added over here? Nothing. Math word for nothing. X would be for something we don't know. We know it, it's just not there. 0. I can add 0 on the end here, and I didn't change my equation. So our k is actually 0. It's not being shifted up or down in any way, shape, or form. It is just being stretched and scooched to the right. So if it's not there for something that's being added or subtracted, it's a 0. If our a is not there, that's when we have a 1. It's called the multiplicative identity versus the additive identity. Not words you need to know off the top of your head, just a thing. Tossing out a little vocab at you. Ka-chow. So what we're going to do to get our points to graph, we are going to take our x values from our log, and we are going to add our h. So I'm going to take all these x's, and we are going to add 2. So my 1/9 plus 2. We can do it in the calculator. We can do it, honestly, when it's plus, it's not brutal, because 1/9 plus 2 gives me 2 and 1/9. If you are a decimal person as opposed to a fraction person, that's 2.1. Keep going. 2.1 repeating. So same vibe, 2 and 1/9 or 2.1 repeating. Then we're going to have our 1/3 plus 2. It's going to give us 2 1/3 or 2.3, blah, blah, blah. We're going to take our 1 plus the 2 to get 3. 3 plus the 2 to get 5. And 9 plus the 2 to get 11. And then we can also go, hey, wait a second, I've got my asymptote right there. It's an x. We can also do our transformation there. I can take my x, which is equal to 0, and add 2 to get that my asymptote's going to happen at x equals 2. It also is just doing the transformation that's here. So I took my asymptote and did the transformation on it. We can do that to it just like we can do it for the transformation over here. X equals h on this case. So then we're going to do our y transformations, and it's the very same vibe. I'm going to take my y's from over here, and we're going to run it through these transformations. I'm going to take my y's times 2 plus 0. So my -2 times 2 gives me -4. That is the wrong color, blue. There we go, now it matches. My -1 times 2 plus 0 is -2. My 0 times 2 plus 0 is going to give us a 0. Our 1 times 2 gives me a 2. And our 2 times 2 gives me 4. So that gives us all the pieces we need to plot. The first thing I'm going to graph is I need to graph my asymptote. We do have to draw in the asymptote. You have to plot the asymptote. You have to draw the asymptote. You have to put the asymptote. At x equals 2 means we have a vertical line right here. Traditionally, we do our asymptotes as dotted lines. You can do it as a solid line, like if it bothers you to do dotted lines, totally fine. You can do it as a solid line. I won't. It hurts my brain. So I always do our asymptotes as dotted lines, but as long as you do it and don't crash through it like the Kool-Aid man. So then we're going to plot up our points so we can see what's happening with our transformations here. So we're going to have our 2 and 1/9, so just barely past our asymptote at -4. So we're down here. 2 and 1/9. There we go. And when we have graphs that are this big, our boxes wind up very, very small. So do not fret about the fact that my 2 and 1/9 at -4 and my 2 and 1/3 at -2 look like they're darn near at the identical x. They're very close together. They're very, very similar, and that's okay. We're just going to be really careful, because then we get our 3, 0. Then we're going to have our 5, 2. And then we're going to have our 11, 4. And when we connect these up, and we still hug that asymptote here, we have our transformed logarithm. And our line should look like this. And again, we can say that this is our transform function by doing light blue line, dark blue line. I can come in here and label this guy my g of x, because that's what we called the transformed function. Make it clear which one we're talking about here. So one thing I want us to notice on our transformed function here, since this had that vertical stretch, the easiest place to see that it did in fact get that stretch is to look at these 3 points right here. When we look at our transformed graph, those 3 points are farther apart. So they went from really close together like this to a little bit farther away. So that's where this stretch is coming into play, right there. Okay, that's the easiest place to see it. Because this whole graph, the light blue graph, it's like I grabbed onto it and I stretched it up and then I pulled it to the right. So we stretched it up and then we scooched it over. I don't know why this rug is trying to take me out today. That is the second time I have almost tripped over the edge of this rug. It's not even curled. I don't know. You can see this. I almost tripped on that thing twice so far today. So a lot of times on these, we're going to ask you domain and range, but only of our transformed function, just because otherwise it's too much. So our domain on g of x. What is our domain of our transformed function over here? On the dark blue one. What's the smallest our x's can go? 2. And what's the biggest they go? Infinity. We get as close to 2 as physically possible without being 2. And our range is the same for every single logarithm. Negative infinity to positive infinity. Yep. Our parent functions are always going to have that domain at 0, so it's going to shift based on where our h is. Our domain is always going to have h to infinity, and for us, we are only ever going to see h to infinity. There exist ways to do it the other way. I'm not saying that they don't exist, but that's more of a pre-cal thing because it's a different kind of transformation. So we're only going to see them with h to infinity. In pre-cal, you see the other ways of doing the transformations, and if you come to my pre-cal, I'll show you how to do it. But we're only going to do like this. We will have some reflections, just not this reflection. We're not going to do the Y reflection, the single ladies reflection. Okay, questions on this one? We are going to do another one. So, yeah. But questions on this guy? Because now we've seen an A transformation. It's exactly the same as how we do it with all the other things we've ever done A transformations on. But I still like for us to see them before we, like, full tilt boogie. Because the next one is full tilt boogie. Next one's full tilt boogie. We're going to do all the things. We've got our f of x. We have log base 2 of x. We've got our g of x, which is minus 1/2 log base 2 of x plus 4 plus 2. We are going to graph it. We're going to find a parent function. We are going to identify our transformations. We're going to find all the stuff. Whew, it's a lot of things. Where do we start? The 2. We got to start with our base. We've got to start with that b. So we are going to start with our 2. That gives us the base for our exponential piece that we need to find our logarithm. Otherwise, we have to do so many logs, and they're icky. We don't like them. And that's okay, and that's normal. But if we do as the inverse, we don't have to do them as logarithms. We can do them as exponentials, which are so much more familiar. So we pick our x's, like -2, -1, 0, 1, and 2. Can you see that one? Or is that too pale? I can see it mostly. Our y values for this, or actually we're going to have our, whoa, chonky pen. Try that again. Exponential functions have an asymptote at y = 0. And our y values for our 2 to the x, we're going to have our 1/4, our 1/2, 1, 2, and 4. Again, our exponential functions, we're not really going to graph. But we just need that there so that we can use that to help us find our parent function for our log base 2 of x. This is the parent function we really need to have. The easy way to get it is to use our exponentials, where we pick our x's to find our y's. If we do not do the exponential first, you are going to have to figure out where we need our x's and probably get some decimal answers. And honestly, it's going to be unpleasant. So I don't recommend it. Do it this way. Find our exponential and then take our inverse. So things that are in the y column become our x's. So our x's are going to be our 1/4, our 1/2, 1, 2, and 4. Everything that was a y becomes an x, so our asymptote is going to switch to an x equals. For our y's, that comes from our x column from the exponential. So everything that was an x becomes a y, so we get our -2, our -1, 0, 1, and 2. Again, I am going to graph our parent function, so we are going to graph our f of x. That's this guy, that guy we just made, our parent function. With our parent functions, I almost never graph our asymptote because it is on the axis. It's this guy right here. So as long as our parent function does not crash through our y-axis, we are good to go. So we're going to have our 1/4 -2, our 1/2 -1, 1, 0, 2, 1, and 4, 2. So this is our parent function. And this is our f of x. Questions on that one? Because then we need to find our transformed function. So one more graph to do. So we need to be able to take our x's and add h. And always remember how much graphing makes us yak, ya plus k. That means I need to know what a, h, and k are. So what pieces do we see up here? What pieces do we have?
The 2 is k.
Mm-hmm. Yep. Okay, so let me mark them down. So our k is going to be this 2. What does that mean is going to happen? What does a k of 2 tell us is happening? it's gonna go up. It's gonna be shifted up 2. What else do we have up here?
The -1/2 is A.
Our negative 1/2 is our A. What does that do? Minus 1/2. What did you say again, my dear?
It goes left or down.
Yeah, this is what that negative makes it reflect. That's when it's going to flip. That's our reflection across the x-axis. When it's negative, just like with parabolas, we had a happy face parabola versus a frowny face parabola. Where it was happy or sad. This is going to be up or it's going to be down. So it's going to reflect across that x-axis. And what else does it do? Because it's just 1/2. It's just the baby. It's so little. What are we going to do to it? It's so little and cute, I want to squish it. It's compressed. So it's so little and cute, you just got to squish it. So when it's little, when it's a small number like a fraction, smaller than 1, it's so little and cute, you want to squish it, it's compressed. So this is going to get flatter. One last piece that we need before we can do the rest of the mathing. Yes, our 4, which is involved with our h over here, and it needs to have that opposite sign. So our h is -4. It always has that opposite sign. H is trying to trick you. So it's always going to be the opposite sign. So which direction is our h going to go? It's going to pull it to the left. So what we're going to do to get our transformed function is we are going to take our x values from our parent function and add our h. We're going to add that -4, so that means we're going to subtract 4. And we're going to take our y's from our parent function times a plus k. So times that 1/2 plus 2. I highly recommend using a calculator on these. Don't need to make it harder for no reason. So we're going to have our 1/4 minus 4. 1/4 minus 4 is going to probably give you a fraction. And if you hit the 2 arrows above the enter key, it should give you minus 3.75. The little, trying to find a place to write. The button that switches it from a fraction to a decimal looks like these guys. So this is the button you want to hit to switch your fractions to decimals. We should get minus 3.75. So make sure we know how to do this, because negative, 15/4 is not necessarily the easiest thing to eyeball. If you can do that, more power to you. But most people can't say negative 15/4. Oh, I know where that is. Not without a little bit of work. So then we do our 1/2 minus 4. And we're going to get our minus 3.5. We're back into the world of whole numbers. We like them. They're a little easier to do mentally. We're going to have our 1 minus the 4, which gives us a -3. 2 minus 4 gives us a -1. And 4 minus 4 gives us a 0. And since we're right here, we can also do our asymptote, because it's an x. It also gets this same transformation, where I'm going to take my asymptote and we are going to add our h, or in this case, subtract that 4. So our asymptote's going to happen at x equals -4. Yes. Yes, you are right. I am wrong. That should be a -2. I am wrong. I'm wrong. 100%. Yep. That's called I was autopiloting and thinking while talking, and that is not always a smart choice for me. If I try and think and talk at the same time, chaos. So now we should be right. Now it should match up. So then we do the same thing with our y's. We're going to take our y's from over here, and we're going to put them through this. We're going to take our y's times our a, so times that minus 1/2, plus our k, plus 2. So -2 times -1/2, and then plus 2, we should get a positive 3. When we type our -1 times the -1/2, and then plus 2, we should get 2.5, 2.5. When we have 0 times our -1/2 and then plus 2, we should get a positive 2. Anything times 0 is 0. Our 1 times -1/2 and then plus 2, we're going to get 1.5, or 1.5. And 2 times -1/2 plus 2 is going to give us a positive 1. So we can see here that our y values are very, very close together. They are squished in. So when it comes time for us to graph these, we're going to be careful. We are going to graph our asymptote first before I put any of my other points on here. Our asymptote is that wall that we cannot crash through. Think Kool-Aid Man style. It's at our x equals -4. It is always going to be at that h value for logarithms. And then we can plot up our points using our table, our -3.75, positive 3. It's going to be right up here. And these are very close together, so we are getting like the vibe of the point. Do not fret about how close together my -3.75 is about to be to my -3.5, which is at 2.5, which means it's kind of right there, so they're kind of connected, it looks like already. Kind of like a little peanut looking thing. Then we have our -3, positive 2, and we wind up with a teeny tiny little baby caterpillar because my dots connect because I got a chunky pen. And then we've got our -2, 1.5, and finally we get a little space here. Woohoo! And then our 0, 1. So this thing has been really, really squished together. We're still going to approach that asymptote, so we still have our line that goes up like this and goes through our 3 points, and then it's going to go this way. I'm just trying to make it a little bit chunkier so we can see it. And this is our g of x. So the last piece on this one is we are going to find our domain. What is our domain on our transform function here? Absolutely right, -4 to positive infinity. Because our very smallest x's are really, really right next to that -4. And I can keep going and 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 going. What's our range? Yep, -infinity to positive infinity. That will always be our range for logarithms. Every single time. So make sure you make it clear which one's your parent function and which one's your transform function, whether you do it with labels, whether you do it with 2 different colored pens, very light pencil versus dark pencil, black pen versus blue pen. I have colored pencils, whatever it is that you need, I can help you do that. But that gives us our transformed graphs. There are 2 more in the packet that you can use as extra practice. We've got 2 on the homework that we also will do as practice. But we're not gonna take another day to do graphing. We're gonna start on our next part of it tomorrow. So you guys can now finish out homework 1. We can do everything we need to on those graphs. We are having a skills check next week, so a week from yesterday. And then a week from today is the last day before spring break. Yes, dear. When you're putting in our negative, use that guy. Because if you use this, it's gonna take your previous answer, so it's trying to subtract from this error, and it's trying to go from there. So if I delete, and switching that out just to be the negative. That's the only thing I changed. Nope.
I think the other one is a minus as well as negative.
Times negative. There we go. Yeah, so when we're doing a negative number, do this. The calculator views them as separate thoughts as being the subtraction. So you can either do, on this one, you could do plus -4. That one would absolutely work, or we could do the -4 on that.
Okay.
But when we're dealing with the negative numbers, use that.
Okay.
Mm-hmm. Have a great rest of your day. See you tomorrow. Bye. Yeah. I love it. Thank you, dear. Saving me from myself.